So now let us see what we have to do. Suppose I take this x1, x0, y3, y2, y1, y0, and I tell you both these numbers are 4-bit 2's complement numbers. Okay, x0, y0, x1, y0, x2, y0, x3, y0. Right? Then I shift and add. I'll just write one more row. x0, y1, x1, y1, x2, y1, x3, y1. What is this term here? What is this term here? Huh? It is x3, y0, because I have to sign extend all these partial products. Right? So this also has to be x3, y0. This is x3, y0. x3, y0. Similarly, this I have to do x3, y1. x3, y1, and so on. Very evidently, I need to throw in so many more adders if I have to do it this way. Okay, and therefore, let's not even go down that alley. It's a waste of time and it's not even going to be efficient either in speed or in performance. I mean speed or in area. Okay, so let's see how to overcome this problem in a more intelligent way. I want to do z equal to x into y. Okay, what is this? This is nothing but minus 2 power n minus 1 x n minus 1 plus summation I equal to 0 to n minus 2 xi 2 power I multiplied by minus 2 power, let's assume now both are n-bit numbers. Okay, because the focus is not on n and m now. Y n minus 1 plus summation yj 2 power j. J equals 0 to n minus 2. Okay. What I'm going to do is, I'm going to write out this negative term multiplication separately from this positive term multiplication. Okay. So this first term minus 2 power n minus 1 into minus 2 power n, that will vanish. Right. You will get 2 power what? 2n minus 2 into x n minus 1 y n minus 1 minus 2 power n minus 1 x n minus 1 summation j equals 0 to n minus 2 yj 2 power j. Then third term minus 2 power n minus 1 y n minus 1 summation I equal to 0 to n minus 2 xi 2 power I plus the positive term multiplication now, which is summation xi 2 power I summation yj 2 power j. Now this is basically my usual multiplication, unsigned multiplication, and therefore I can go ahead and just do it normally. This also is a positive number, therefore I have nothing, no problem. Only place that I have to worry about are basically this negative term and this negative term, right? Wherever you get the highest MSB of either x or y, right, and the other term is not the MSB, then it is a negative number, and therefore I have to handle that slightly differently. Okay, so what we'll do is we'll do exactly that in the following multiplication: x3, x2, x1, x0, y3, y2, y1, y0. right? So I will just write this x0, y0, x1, y0, x2, y0. Positive numbers, no problem. Similarly, x0, y1, x1, y1, x2, y1. Here again, this is what? x0, y2, x1, y2, x2, y2. Now I will not write the other terms because the moment it involves x3 and y3, I have to be careful. Okay? So we'll see what that is. If I took this y3 term, normally it would have been x0, y3, x1, y3, x2, y3. We'll leave the x3, y3 out because that's again a positive number, right? This is now a negative number. How do I make a number negative? You have to take 2's complement of that number, which means you invert them and add 1 to it. So I will invert these numbers. Of course, these were zeros earlier. I am going to now make these 1. Right? Similarly, there is this x3, y0, x3, y1, x3, y2 term, which will come here again, right? This is x3, y0, x3, y1, and x3, y2. That's also a negative number. I will invert that also. This is 1, 1, 1. I am not putting the ones on the left yet because we don't know how many bits we need. We'll come to that. And then what should I do? I need to add a 1 because you invert every bit and then add a 1. That's how you get the 2's complement number, right? That's what I want to do here. Right? Now I have this x3, y3, which is a positive number. No problem, right? So I need to put one more 1 here, and of course I can get a carry. Therefore, I am going to append 2 more 1s on this side. This is 0, and all these bits are 0. Okay? All we have done is taken the negative numbers separately and written it in its 2's complement form, complemented every bit and added 1 to it. Now there are a bunch of hard-coded 1s. You perform the addition beforehand. I have to add 4 1s. What will I get? 0, and a 1 will carry over here. 2 1s. 0, alright, 0, and a 1 will carry over where? 2 bits away. So you will get a 1 here. No, that's not 2 bits. This is 2 bits. Correct? 1, 2, 3, 4. Okay. If you add these 2 1s, you will get a carry 1. 4 1s if I add, I'll get 0, 0 and a 1 there. Right? Now similarly you come here. That addition is done. I have some 1 dangling somewhere. I have to take care of that in my multiplier. Add these 2 1s. You get a 0 and then you get a 1 here. So you get what? 1, 1. Now you simply rewrite this by wherever there was x0, y3, x1, y3 or x2, y3, you simply complement it. Right? And you got to add this 1 and you got to add this particular 1 into my adder there. Right? Therefore, you will find that in order for me to do signed multiplication, all I have to do is make this x3, y1, wherever there is x3, yj, where j is between 0 and 2, complement the bit. Or wherever there is y3, xi, and I is between 0 and 2, complement the bit. That's what you see here. In that half adder, that's why I said retain that half adder. Because when I go to signed multiplier, I have to put now that 1 here. Right? In my previous thing, I showed you that there is a 1 here. Right? Along with this x1, y3 or x3, y1 complement, I need to add this 1. And that is what is appearing here. Along with x3, y1 bar, I have added that 1 to my half adder. And therefore, that should remain. Now that will cascade correctly to the next stage. Finally, I have to add this 1. Where did that 1 come from? Because I add these two ones, I get 0, and then I add a 1 on top there. So the final carry out generation after adding this x3, y3 with this, so this will give me a carry, right? This addition will give me x2, y3, x3, y2 will give me a carry. That carry along with x3, y3, when I add, right, x3, y3 along with the carry coming from the previous stage, that will give me a carry. And I need to add the 1 to that. Is that clear? So, yeah? Okay, last part. Did you follow this arithmetic here? Why I could... Sure, okay. So, let me write this a little differently now. Okay? I am going to write this a little differently, where x3, y0, I will put it back here. x3, y1 bar, I will put it here. And x3, y2 bar, I will put it here. Okay? So this is like x0, y0, x1, y0, x2, y0, x3, y0 bar. Then I have x0, y1, x1, y1, x2, y2, and x3, this is y1 bar, right? That is basically which term that we got? We got this x3, y1 bar here. That's what I am writing. I am just rewriting that same addition there, right? Then, what's my third term? Partial product. It is x0, y2, x1, y2, x2, y2, and x3, y2 bar. Right? Now there is another term where I am now going to multiply by y3, which is all negative numbers. So therefore here I will write this as x0, y3 bar, x1, y3 bar, x2, y3 bar, and x3, y3. Okay. Now in the process of adding these 4 ones, what did I get? If I add these 2 ones first of all, I'll get a carry of 1. Add these 2 1, I'll get a carry of 1. So the answer is 0 here. So nothing to be done on that row or that column. Now again there are 4 ones. I'll get one more carry of 1 here, carry of 1 here, 0 here. Now 4 ones when I add, I'll get 0, 0, and I have to add a 1 here. So along with my x3, y1 or x1, y3 and x2, y2, I need to add a 1, right? That 1 I am putting here. That addition is done. Those ones, because of the 2's complement addition, we are done. We have ones now on the MSB side, right? So therefore, I add these two ones. What do I get? 0, and I'll get an extra 1 here. So if I do 1 plus 1 plus 1, I'll get 1, 1, right? So I need to add one more 1 there, right? Because finally this 1 needs to go somewhere. Where should it go? It needs to get added to the carry generated from here. So along with x3, y3, I will add a 1. Right? Oh, it's not along with that actually. It's here. Right? That's what we are doing here now. Okay, let me just copy this. Right? So we had 2 ones that we had to add. This one needed to be added somewhere. Where should it be added? It has to be added where you are adding x3, y1, x2, y2 or x1, y3. That's why where we are doing x3, y1, of course that has to become x3, y1 bar. I am going to add that 1. This 1 comes and sits here. After doing addition with x3, y3, there is the carry out. There I need to add this 1. This guy is now coming and sitting here. So all I had to do to my unsigned multiplier was just complement the bits where I had x3, yj, where j was between 0 and 2. Just make it complement bits, right? This bit, and no, not that one, right? Then wherever I had y3xi, where I was between 0 and 2, again, this one, and this one, I made it complement, right? And then I had to add 2 ones. And that's what I have done here. It's quite surprising that with a simple change like this, it's very counterintuitive unless you know what the math is. Okay, otherwise you'll never be able to figure out, how this gives me signed multiplication. Clear? Any questions? Final thing I'm going to leave as, an optimization for you in the project. All through we have done AND gates. But of course, since this is in the critical path, it's better I do NAND gates. If I make everything NAND, then I need to change this. It has to become a half adder prime, in the sense where it takes complements and gives out complements. So when you design your multiplier, please make sure you optimize for this NAND gate as opposed to trying to use an AND gate. Okay? You have to just figure out how to put this. You put NANDs, then you'll have to have a full adder which gives, the complement of sum and carry, then propagate it appropriately. Okay? With that, we have sort of really covered, the key aspects of multipliers. Okay, both signed and unsigned. So both, as I told you, I don't have time, so I will not do it. Right? So let me just quickly summarize again what we did. So the learning objectives for this module, right? Adders and multipliers. Designing full adder with least PMOS stack size using self-duality or mirroring principle. Constructing adder architectures to reduce delay from O of n to O of root n, right? O of root n, up to that we did. square root adder. O of log n you have to do, carry lookup adder in your project. Then timing diagrams to show signal propagation of various adders, that is static timing analysis, arrival times, right? And why we get benefits. Then array multiplier for both signed and unsigned multiplication, that's what we did today. Then optimize the array multiplier using the inverting property, that's what I told you, where if you use a NAND gate instead of AND gate, then you can use this inverting property and optimize this further, right? Then Booth encoding, unfortunately, this time I will not have time to cover it, but it's effectively a way of reducing the number of partial products, right? Right now, if I have n bits, n cross n multiplication, then I have n partial products to add, right? And each partial product, right? If you look at each partial product here, right? If you look at the partial product in the multiplication here, they are just, if any bit y0, y1, y2 or y3 is 0, then the partial product also is 0, right? If it is 1, then the partial product is x, right? It is x shifted by something, right? 2 power k into x, it is shifted by something. So you are generating only two kinds of partial products, 0 and x. But it is possible to generate other kind of partial products easily. Like for example 2x is just shifting, right? Shifting left, right? You can exploit this in order to reduce the number of partial product additions, right? Where for example if you treat this y3, y2, y1, y0 as a base 4 number as opposed to a base 2 number, then you will get only two partial products, but the kind of partial products that you have to generate will be different. That is what Booth encoding is all about. Just a very brief thing about what Booth encoding is. Mathematically, we show why you can actually derive it and optimize it in a particular way there. Okay, you can look at my slides, it's very obvious. Okay, you take a look at my slides, it's all there. The math is worked out, so you can figure it out on your own as well. Okay.